Okay guys, today we're going to be starting to look at atoms nuclei. We're going to start off with the atom. So in junior sciences you would have looked at something similar to this here. We've got a positive nucleus and we've got some electrons orbiting around the outside using the electrostatic force. In terms of physics, what we're going to be looking at is the emission spectra and some other stuff to do with it. So an emission spectra is simply when light gives off a whole bunch of different colours. So it will actually emit light based on the energy of this electron here. Now that electron there likes to be in a certain bunch of spots. It won't orbit at every single radius, but it will orbit at very specific ones depending on what element it is. So these are very good for identifying elements. And that's mostly because every single element has a unique number of electrons, a unique number of protons, and they orbit in really, really specific ways because of that electrostatic force. People found out a long time ago if they had a light source that they heated up, so we get some sodium, for example, the yellow sodium vapor light, the one we use with Young's double slit. The sodium will actually emit a whole bunch of light. It goes through some sort of diffraction grating setup or narrow slits, and the light seems to spread out, and we don't just get yellow, we also get some kind of redy purple stuff, and we get a little bit of green and a little bit of, well, actually quite a lot of yellow that you would have already seen yourselves. And this is because this electron here only likes to exist in discrete energy levels. That's what we call them. So it wants to exist at this point here, and if we add a little bit of heat to it, it might orbit further out here, or further out here, or maybe even further out here. And every single time we add some heat, and that heat kind of goes into moving that electron a little bit, making it go faster, so it orbits a little bit further out, it will actually start to drop back down, and as it drops back down and gets closer back to where it wants to be, where it is in the ground state, it will actually give off different colours, and every single element has its own unique set of colours that it emits. So sodium is mostly white. You would have seen the helium neon laser. That's actually more to do with the emission spectra of one of those two elements. I won't say which one. And it's unique to that element. Basically means that we can fingerprint, whatever you want to call it, the elements that are in an object. So emission spectra or line emission spectra will actually give us different colours based on where these photons come from when these electrons drop back down energy levels. So if you see an emission spectra for sodium, there's a big bit of yellow in the middle, and on one side you'll have some red, on the other side you'll have some blue. Over here I've actually got the the energy level diagram for hydrogen. Now hydrogen is really cool because it's the simplest element, which means that we know a little bit about it, and it means that there's a lot less going on here than there would be for something like tungsten or silver or gold or platinum or calcium or potassium even. What we end up with is a unique set of places. So here's the ground state, n equals 1, so n is the energy level number, n equals 2, 3, 4, 5, blah blah blah, up to infinity. Hydrogen's got about 5 that we really worry about. Some other elements have tens or dozens. So what we start off with is an electron that's 13.6 electron volts below infinity. Basically means that it takes 13.6 electron volts to get the electron to actually reach infinity or be ionized. So we put 13.6 electron volts into hydrogen, and that electron will disappear. So in here, these ionization energies for different elements you would have seen for sodium is only a handful of electron volts, whereas for hydrogen it's actually quite a lot more. What we're going to do is put in a certain amount of energy, and we're going to get that electron to sit here at the third excited state, or n equals 4. And what we're going to do is make that, let that hydrogen go, and we're going to let that electron drop back down. And as it drops back down, it can do that in a few different ways. If it wants to, it can do this, and drop back and give off the difference in energy from here to here as a photon. So this photon is going to have HF, remember E equals HF, is energy level 2, take energy level 1, and in this case it's 13.6, or sorry, it's 13.6 take minus 0.88, and I should have done this beforehand, 12 point something or other, whatever it is. I'm just going to go 12.7 electron volts as a photon that's going to come off at a specific with a specific frequency, therefore a specific colour. This one here, if it's 12.7 electron volts, it's definitely going to be ultraviolet. Now, that same amount of energy could also come back as that photon and that one, or it could come back as that one and that one and that one, or it could come back as that one and that one. Alright, so have I missed one? I don't think so. So you can see that by getting from the ground state to the third excited state, we've got a whole bunch of different photons that are coming out, and sometimes it's this ultraviolet one, sometimes it's this ultraviolet one, but sometimes we'll end up with something like this guy here. So if I look more closely at this one, we're going to have E to take E1 is HF once again, and we're going to have in this case minus 1.5 take minus 3.4 is HF. So we're going to end up with a lot more. What do we got here? 1.9 EV, I think. That sounds kind of right-ish, I guess. 1.9 electron volts is our HF. Now 1.9 is kind of red, so that would actually be a red photon. So when you look at the line emission spectra of hydrogen, what you'll see is some ultraviolet stuff that happens, but you'll also see in the Roy G. Biv section of the emission spectra, you'll actually see a nice bright band of red. You'll also see some light there, and you'll also see another piece of light there. So this last one that I've drawn here, 3.4, the difference between 3.4 and 0.88, yeah, in the high 2s, so 2.6, somewhere there, and that one's also visible. It's kind of a greeny blue colour. This one here is going to be infrared. Now, because we know a little bit about the energy levels in hydrogen, because it gives off all these unique different colours based on, you know, the energy level differences and such, we had three guys. One was called Lima, one was called Bulmer, one was called Passion, and what they wanted to do was start experimenting and detecting, I guess, these different things here, and using those very, very, very specific wavelengths or very specific energies, frequencies of light, to be able to do some observation, some experimentation with. So Lyman, he wanted to deal with everything that ended up here. So all of the light returns to the ground state. And that means, because there's the smallest jump, the lowest energy photon is between n equals 1 and n equals 2, and we've still got, you know, 10.2 electron volts difference just to get from there to there. That's ultraviolet. So that means that everything that drops from higher energy levels all the way down, so remember Lyman's dealing with everything that goes down to the ground state from anywhere up here. He doesn't care about these smaller ones. All he cares about is the ones that go to the ground. All of this stuff is ultraviolet, so that's what he was dealing with. Then the second guy, Bulmer, he wanted everything that went back to the first excited state. So he was getting everything that ended up here. So he wanted this photon, and he wanted this photon, and he wanted the one that came from 0.54 down to 3.4. So he was actually dealing with stuff that's, you know, in a few electron volts. So his stuff was actually visible. Passion dealt with everything, or dealt with, that ended up at the second excited state, or n equals 3, and all of this stuff was infrared. Alright, so these three guys had, you know, three different niches, I guess, that they wanted to look at, and it was all to do with the line emission spectra of hydrogen, simply because we knew a little bit about, or they knew a little bit about it at the time, and they wanted to be able to use these very, very, very specific energy levels to see what they could actually do with them.